Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Go ahead and raise your hand if you did not get a red mark for today. Or get a red mark? Let's go ahead and get started with our discussion. So we need to be able to simplify radical expressions, right? Whether they contain numerical factors only, variable factors, or a combination thereof. So when we look at number one, we know that that fourth root isn't fully simplified if there are any perfect fourth powers hiding out inside of it. So it appears as though we can break this up into several perfect fourth powers. Is 1250 a perfect fourth power?
Yeah.
No, but it contains one, right?
No.
It contains one. What's the greatest perfect fourth power that divides evenly into 1250 without a remainder, Margot? 625. So let's go ahead and rewrite this fourth root. Let's go ahead and rewrite this fourth root as a product of factors where I do have perfect fourth powers. I know they'll simplify to integers or powers with integer exponents out front. So here we go. So we're going to break up that 1250 into, Margot says 625 times 2. This current x power, x to the 10th, right, has an exponent that's not divisible evenly by that index on the radical of 4. So we'll chunk that down into a product. I could rewrite that as x to the 8 times x to the 2nd. Do you agree that this red product, x to the 8th times x to the 2nd, is x to the 10th? Yes, but by writing it as x to the 8, I know this first power will reduce to an integer power up front. X to the 8 divided by 4, the index on my radical, will be x to the 2nd. So I know that's going to reduce out front. Meanwhile, I still have a y cubed underneath. That's not going to reduce. Its current exponent 3 is less than the index on the radical 4, so it's going to be stuck for the remainder of the problem. But the z to the 13th certainly will reduce. This z to the 13th has an exponent that's higher than 4. 13 is not divisible by 4 evenly, but I'll chunk it into a product of powers. Let's say z to the next highest exponent beneath 13 that is divisible by 4. 12 times z to the first. And so I've rewritten my quantities inside as products. Now every single factor that's a perfect fourth power inside of my fourth root will reduce to an integer or a power with integer exponent out front. Let's do it. Here we go. So that 625 is a perfect fourth power, x to the 8th. Z to the 12th, did we get them all? Out front, we'll have the fourth root of 625. Everybody find it. Look at your half sheet. No calculator. Look at your half sheet. What's the fourth root of 625? Tyler?
5.
5, thank you. So we've got 5 out front. What's the fourth root of x to the 8th? Katie? X to the 2nd, thank you. What's the fourth root of z to the 12th? Get ready. Adam? Z cubed, good job. Still have a fourth root, and inside that fourth root we have 2x squared y cubed z all inside, close radical. Let's take a look and see if I messed up. And raise your hand if you had the same thing. So did everybody get all the way to the end? You did. You guys are doing much better than last class. So now we've had a couple days dealing with radical expressions, and you guys are really improving. So way to go. Keep up the good work. Let's go ahead and take a look at our second one. In our second one, we have a fraction, right? The F word. We're not allowed to have a fraction inside of a radical expression and still be fully simplified. And so while 3/8 is not a perfect square, right, we could go ahead and break this up into a quotient of individual radicals by applying the quotient property to radicals. We'll go ahead and rewrite the square root of 3/8 is equivalent to the square root of 3 over the square root of 8. Now we'll go ahead and try to reduce. Does 3 contain any perfect square factors? Nope, that's done. Does 8 contain any perfect square factors? 8 does contain perfect square factors. And so right now, we're at a fork in the road. We could decide, do we want to simplify the square root of 8 first and then multiply by a smaller problem radical for our rationalization of the denominator, or do we want to multiply by root 8 over root 8 right now? And either one is acceptable, so long as you know if you don't simplify first, you're going to have to simplify after. I like to simplify first to make smaller numbers. If I'm working without a calculator, I like to work with smaller numbers, but that's just me. And so you're welcome to multiply top and bottom by the problem radical, the square root of 8 right now, to rationalize the denominator. Just know that you'll have to reduce later multiple times. So I'm going to go ahead and simplify. I'm going to keep simplifying. I'm going to rewrite that square root of 8 as the square root of 4 times 2. Then I know a 4 inside the square root is going to come out as a 2 out front. So by reducing my square root of 8 into 2 root 2, I'm going to have a smaller problem radical, right? I'll have a smaller problem radical. So my problem radical now is not the root 3, it's the root 2. It's not okay to have the radical in the bottom of a fraction, right? That's not fully simplified. So we'll go ahead and multiply top and bottom by that problem radical in a technique known as rationalizing the denominator. That's our strategy for getting rid of a radical in the bottom of a fraction, so I can be fully simplified. And now we'll go ahead and multiply straight across. So here we go. Root 3 times root 2 is root 6. Because they're both radicals, I can apply the quotient property. Root 6 doesn't contain any perfect square factors, so that's not going to reduce. That's the end of the road for that. 2 times root 2 times root 2. Oh, goodness gracious. So let's do the root 2 times root 2 first. Gives me 2. So on bottom I have 2 times 2. So we must get root 6 over 4. Now we could have multiplied by root 8 over root 8 back at this green step. Then we would have gotten root 3 times root 8 is root 24. Have to reduce that. We would have gotten 8 on the bottom. After reducing the root 24, we'd go ahead and divide out the common factors appearing in both the 8 and the reduction on top, and we'd still get root 6 over 4. So either one is perfectly acceptable. At the end of the day, however, we need to get the same answer. Go ahead and check yours, and raise your hand if you got root 6 over 4. Can we get all the way to the end? Good. If you didn't, you probably need to reduce your root 24, or divide out a common factor with the 8 on bottom, and then you'll get here. What questions do you guys have on number 2? Okay, let's continue the party then. Number 3, holy smokes, we've got lots of radicals floating around here, lots of powers. That's okay, I can apply the product property in reverse. That is to say, the fifth root multiplied by another fifth root can be rewritten as a single fifth root. Let's go ahead and do that as my first step. So we'll rewrite it as a single fifth root, and inside we'll have 2 times 16 is 32. A to the 4th times A to the 4th is A to the 8th. B to the 3rd times B to the 2nd is B to the 5th. And now we'll go ahead and try simplifying. It looks to me like we've got several perfect fifth powers hiding inside this fifth root. It looks like 32 is a fifth root already. All right, that's already a fifth root. So go ahead and tell the class what the fifth root of 32 is when I call them. So what's the fifth root of 32? Eric? 2. Thank you. That's simplified. 8 and 8. You guys want to do the shortcut now? Want to do the shortcut for our radical simplification? The current exponent on the a term, 8, is greater than the index on the radical. I know this will simplify, and I'm going to get an a power out front. But how much? Well, let's see. A to the 8 divided by 5. How many times does 5 go into 8? How many whole times? 1 whole time, so I must have a to the first out front. With how many remaining? Well, 5 goes into 8 1 whole time with 3 remaining. And so inside, I'm guaranteed to have an a cubed still remaining. And now my index is less than the, my exponent a to the 3rd is less than the index on the radical. That's not going to reduce anymore. B to the 5th. Inside a fifth root, that's already a perfect fifth power. That's already a perfect fifth power. And so I know that b to the 5th is going to reduce b to the 5 divided by 5 is b to the 1st. And so my final answer would be 2ab, fifth root, a cubed. All right, we got it all. So to perform our shortcut for simplification, we can treat this index on my radical as a fraction, a 1/5, and then do a division. 8 divided by 5, or 8 times 1/5, right, is 5 goes into 8 1 whole time with 3 left over. Awesome. What questions do you guys have on number 3? All right, let's go ahead and take a look at our notation. So we can rewrite a fractional exponent with radical notation, or we can write radical expression with a fractional exponent. Let's do each. So rewrite with radical notation, we can do that 2 different ways. X to the 2/3 power could be rewritten as the cube root of, and then x squared. Or we could rewrite this as the cube root of x, and then all squared. Either is correct. However, they'd be distinctly different order of operations. In evaluating x to the 2/3 in the first expression, I would first square x and then find the cube root of it. Yes? Versus the second expression, I would first find the cube root of x and then square that. which of these two expressions, 1 or 2, would be easier to do non-calculated? Right? Which of these two expressions would be easier to do non-calculated? Ben C? The second one. By doing the cube root of my input x first, I'm making a smaller number than radians in second. You should be able to do each of them. They're equivalent, right? They're equivalent, so either one would be fine. Awesome. And lastly, rewrite with rational exponents. That's where I treat my radical as a fractional exponent. So that fourth root could be rewritten as a 1/4 power, so long as we assume positive variable-based x's and y's. So here we go. I could rewrite this as x cubed y all to the 1/4 power, right? I could rewrite that as x cubed y all to the 1/4 power by treating that fourth root as a 1/4 power. Everybody see that? As a fourth root. And then if I wanted to, I could apply that 1/4 to each one and get rid of parentheses. That is to say, x cubed to the 1/4 power is x to the 3/4 and times y to the 1/4. So either of these expressions is correct. So either of these expressions is correct. Awesome. What questions do you have about today's Bellwork? Okay, then let's go ahead and check our homework. I'll pause the recording now. Today we're going to solve equations involving radicals. Okay, we're going to solve equations involving radicals. And much of the techniques that you've learned earlier with power functions is going to be applied today when you solve these equations involving radicals. Because as you know, you could rewrite a radical expression, like our Bellwork, as a power expression, that is with a rational exponent. So like a fourth root is the same as a 1/4 power, and we already know how to undo exponents. We can purposely raise both sides to the reciprocal exponent. So we'll be working with that. One key difference is we need to look out for what we call extraneous solutions. Extraneous solutions was part of your reading question. So if in the course of using our inverse operations, right, we multiply both sides, we raise both sides to an exponent, we could create potential solution values, right, to satisfy your final statement, but don't satisfy your original statement. So we're going to look out for that and see when that could arise during today's class period. The next thing we need to know is that when we rewrite, when we have a radical expression, we're now allowed to have negative bases for an odd root, and so we can have solutions if a negative is inside of an odd radical. We're allowed to simplify it. If we have a negative constant that a odd root is set equal to, we'll still have a solution, but we wouldn't if we had a fractional exponent. So we're going to nail that down too, so that you're comfortable handling the different cases. All right. So in general, to solve an equation in the form of a times x to the m over n, where I've got my power written with a rational exponent, plus b equals c, or a equals the nth root of x to the m plus b equals c, right? It's still a question of inverse operations, right? Reversing and undoing our forward steps. So typically we'll isolate that variable or variable expression with the exponent of the root by adding and subtracting, multiplying and dividing to get your power alone on one side or your radical alone on one side. Then you'll purposely raise both sides to the reciprocal exponent to undo the current exponent and get x by itself. Lastly, we want to make sure I check our solutions. So I want you to think about, on your note sheet, I want you to think about how many real solutions are there if we're dealing with a power function, x to the even integer exponent, set equal to a positive number, okay? Go ahead and tell your partner how many solutions we should be on the lookout for number 1. That is x to the even integer exponent set equal to a positive constant. Go ahead and tell your partner. How many solutions should there be for number 1? All right, what do you guys think? Carson and Dakota?
2.
2. Raise your hand if you had 2. 2. Absolutely. And so in general, if we're dealing with the graph of a even power function, this is a situation where we have a parabola shape set equal to a positive constant. That looks like 2 different intersection points, so we're looking for 2 real solutions. Absolutely. So 2 real solutions is what we'd be looking for that first one. Contrast that with an x even power function set equal to a negative, set equal to a negative constant. So now we've got our even integer power function, just like before, but we're setting that equal to a negative constant. Now, how many real solutions do we expect to see for number 2? How many real solutions do we expect to see now? Olivia? No real solutions, so 0 real solutions. No real solutions. Awesome. What if we had an odd power function? An odd power function set equal to a positive number. And lastly, an odd power function set equal to a negative constant number. All right, number 3, odd power function set equal to a positive. How many real solutions do we expect to see? Braden?
1.
1, I agree, so there's 1. And how many solutions do we expect to see for an odd power function set equal to a negative? Logan? 1 as well. And so if we have an odd power function, then we're always going to have one real solution. Awesome. I think I'm going to put 0 real solutions here. I don't want the none and the 1 to overlap. It's the little things. It's the little things. All right, now let's go ahead and rewrite our power function with a rational exponent. Consider we had x to the fractional exponent. We're dealing with an even, like a 1/2 or a 1/4, right? Or a 7/8. Set that equal to a positive constant. Can we find some real number x when raised to the fractional exponent that will equal a positive number? Absolutely. This would be like the 4th root, right? The 4th root of x equals 4. Oh, the 4th root of 64 I'm sorry. This would be like the cube root, the 4th root of 16 equals 2. Well, if x were 16, then that would be true. And so this is absolutely possible. We would just have one real solution. However, if I have that fractional exponent with even denominator set equal to a negative, right? This would be like the 4th root of x equals a negative 2, then there's no way, right? We're not allowed to have a negative base in that fractional exponent, and so there's zero real solutions here. X to the one odd power, the cube root of x equals 4. Oh yeah, and then x would be 64, so that's no problem. So we've got one solution there. And then the final case, because of fractional exponents, we're not allowed to have negative bases. Therefore, there'd be no real solutions if we've expressed that equation with a fractional exponent. We're only allowed to have positive bases. Therefore, there'd be no way we could set a negative result there. So again, 0. However, in the same way, if number 12, if you look right across from number 8 on your note sheet, number 12, if we were to rewrite that fractional exponent as an odd indexed radical instead, then we're allowed to have a negative answer. And so this number 8 and number 12 are your big ones to pay attention to. Let's go ahead and show you what I mean. So even radical set equal to a positive number, certainly. We've got one solution there. Even radical set equal to a negative output, no way. 0 solutions. Odd radical set equal to a positive output, certainly. One solution. And now, that's right, the moment you all been waiting for. An odd index radical set equal to a negative. Now we're allowed to have a negative input there, which will make your output negative. So yes. So the key difference here is the difference between number 12 and number 8. It's not okay to have a negative base if we write our exponent as a fraction. It is okay to have a negative base if we have an odd index radical. Okay, so number 8 and number 12 are the big ones to pay attention to. All right, now let's go ahead and see about solving some equations using our inverse operations. So in general, to solve a radical equation, we want to add or subtract, multiply or divide to get the radical alone on one side, and then undo our radical by raising both sides to the reciprocal exponent. Okay, so let's go ahead and take a look at the first one. Is my radical all the way by itself in letter A, Heather? No. So I first want to use inverse operations to isolate it. It looks like my best first step would be to undo that multiplication. And so I'm going to divide both sides by 6 as my best first step. Here we go. Here we go. When I do that, we get the cube root of quantity x plus 1 alone on one side. On the right, 18 divided by 6 is 3. And now we're going to go ahead and undo that radical. If we consider that radical, that cube root, as a 1/3 power, we could raise both sides to the reciprocal exponent, the 3/1 power. In other words, we're going to cube both sides to undo a cube root. Yes, that's right. We're going to cube both sides to undo a cube root. Thank you for showing that. So when I cube a cube root, I get the quantity x plus 1 outside of the radical, where I can deal with it. When I cube the right-hand side, I go to my half sheet. Go ahead and tell the class what 3 cubed is, Dakota. Thank you. And now I can finish it out using our regular inverse operations. It looks like a subtraction. We'll seal the deal. And my final answer appears to be x equals 26. Awesome. Let's go ahead and do the same strategy for letter B. So is my radical currently isolated on one side of the equation right now? No, we've got some work to do. So first step, let's do a subtraction. Subtract 10 from both sides. That will get, don't forget about the negative. -3 I still have times the 4th root of quantity 2x minus 5. Close radical equals 9. Next, we want to go ahead and undo that multiplication by -3 in front of the radical. So we'll divide both sides by -3. Thank you for showing that. That will get our radical alone. Hooray! 2x minus 5 equals, and 9 divided by -3 is -3. And lastly, I'll undo that 4th root. So last problem, we saw we undid a cube root, right, by raising both sides to the 3rd power. Guess what? We're going to undo a 4th root by raising both sides to the, you guessed it, 4th power. So by raising both sides to the 4th power, we'll undo a 4th root and get that quantity, 2x minus 5, out of the radical and on the ground floor where we can deal with it. Meanwhile, on the right-hand side, we're doing -3 times itself 4 times. So -3 times -3 times -3 times -3. So that's going to be a positive, and then 3 to the 4th. That's on your sheet. So what's that, Brady? 3 to the 4th. 3 to the 4th on your sheet? 81. 81, thank you. Awesome, so we're almost there. We'll go ahead and add 5 to both sides. Add 5 to both sides, so 2x equals 86. Is that right? 86? And then divide both sides by 2. So it appears as though my solution value is x equals 43. 43. Awesome. So we've isolated the radical expression by performing our regular inverse operations, adding, subtracting, multiplying, dividing to get the radical alone. Then we undid a radical by raising both sides to an exponent, the reciprocal exponent. And then we finish it out of the way. Now we need to go back and check our solutions. So we'll go back and check our solutions just like we always do by taking our potential solution value and plugging it into the original. If it makes a true statement in the original, then I know it's a solution to that original equation. If it does not, right, then it's not a solution. So let's check that x equals 26. Into my original, everywhere I see an x is 26 plus 1 is 27. Then the cube root of 27 is that on your sheet? Cube root of 27? 3. Is 3. Then 3 times 6 is 18. Does it make a true statement? Yes. And so x equals 26 is a solution, a real solution. Let's go ahead and check x equals 43. Take 43 and put it in the original. 43 in for x. 2 times 43 is 86. 86 minus 5 is 81. The 4th root of 81, everybody find it. So what's the fourth root of 81? Hang on. Katie?
3.
3. So now I have 10 minus 3 times 3 is 10 minus 9. Does that equal question mark 19? Does 10 minus 9 equal 19? No, and so here we've generated a potential solution value, x equals 43. We followed the math rules and order of operations and reverse and undo, and yet it does not satisfy the original. And so it turns out that this is what we call, like your reading question, an extraneous solution. Okay, an extraneous solution. It's a potential x value, right, generated in the course of my inverse operations for solving that does not satisfy the original. It is not a solution. It's what we call extraneous. And so we've generated it. Now we're going to go ahead and label it as an extraneous solution. Extraneous, and there are no real solutions. So because my generated x value 43 did not satisfy the original, it's what we call extraneous. We label it as such, and we write no real solution for our answer. Let's go ahead and take a look back at our work and see if we can identify a turning point where we could have seen that there would be no real solution. If everybody looks at this red line here, the fourth root, right, an even index radical, 2x minus 5, the fourth root, set equal to that negative number, right? How many solutions do we expect when we have a even index radical set equal to a negative number? How many real solutions do we expect? 0 real solutions. And so if in the course of our solving equations we generate an even radical set equal to a negative, then we can expect no real solutions, right? We can expect no real solutions because there's no real number that's going to make that true. All right, so let's go ahead and try some more. Let's do 8/5 times the 6th root of m equals 8. Again, we need to isolate my radical before I can undo that radical. So the first thing I would do is divide both sides by 8/5, keeping in mind that dividing by a fraction is the same as multiplying by the reciprocal. And so dividing by 8/5 is the same as multiplying both sides by what? It's the same as multiplying both sides by what? Aaron? 5/8, thank you. So we'll multiply both sides by the reciprocal, 5/8, first step. Multiplying by a fraction, we do that straight across. So I get the 6th root of m alone equals, and then we'll go ahead and reduce. 8 divided by 8 is just 1 times the 5 is 5. Or straight across, 8 times 5 is 40 divided by 8 is also 5. So I've got the 6th root of m equals 5. Do I have an even or odd index radical? An even or odd index radical? Margo?
Even.
Even. Is it set equal to a positive or negative output? Is it set equal to a positive or negative output? Mark?
Positive.
Positive. Do I expect to see one real solution or no real solution? Do I expect to see one real solution or no real solution when I have that even set equal to a positive?
1.
Cody?
1.
1. And so we expect to see a real solution. Let's find it. How do I undo a 6th root? Easy cheesy. We'll raise both sides to the 6th power. We'll raise both sides to the 6th power. Go to your sheet. When I raise both sides to the 6th power, I've got an m alone, and what's 5 to the 6th? Everybody find it? Tell the class when I call on you. Go to your half sheet, Barrett. 15,625. Woo! Thank you. I'm not going to box it. I'm going to check it. So I'll go into my original. The 6th root of 15,625 is 5. 5 times 8/5 is 40 divided by 5. Does that equal question mark 8? Yes, it does. This is a solution. It's not extraneous. It satisfies the original, and it's a real solution. And we expected that because once we had the radical isolated, it was an even root equal to a positive, so we expect one positive. Let's do 2. Ready? First step. Subtract 18 from both sides as we get closer to isolating the radical. I still have the negative here, so let's keep that for one more step. 9 minus 18 is negative 9. How will I undo the negative? I'll just multiply both sides or divide both sides by -1 to isolate my fourth root. The fourth root of u now equals negative divided by negative equals positive. Do I have an even or odd index radical? Even or odd index radical? Luke. Even. Is a set equal to a positive or negative number? Marina.
Positive.
Do we expect to see one or none real solution? Right? One or none real solutions. Aaron?
1.
1. I can have an even set equal to a positive, and I expect one positive result. So let's go ahead and do it. I'm going to raise both sides purposefully to the fourth power. The fourth power to get u alone. And u equals 9 to the fourth. Find your sheet. Check your sheet. And what do you get for that? Olivia B?
6,561.
6,561 into the original fourth root 9. 18 minus 9. Does 18 minus 9 equal question mark 9? Yes! So we don't have an extraneous solution. We have found a real solution. In number 3, we've got radicals on both sides of the equation. So again, we want to add, subtract, multiply, or divide to get a single radical expression alone on one side. So my favorite first step would be subtract the fourth root of c from both sides. So I'm going to subtract the fourth root of c from the left and from the right. That's like subtracting 1 fourth root of c from 3 fourth root of c, and I would get 2 fourth root of c. Bring down your equals, and I still have the -8 remaining. Now I'll divide both sides by the 2. That would get my radical, my fourth root of c alone. And how do I undo a fourth power? Easy cheesy. I'm sorry, a fourth root. I'll raise both sides to the fourth power. When I raise both sides to the fourth power, I get c alone. And c will equal -4 to the fourth is -4 times -4 times -4 times -4. Andrew?
256.
256. Thank you. Awesome. So I'll go back to my original. The fourth root of 256 is 4 minus 8. Does that equal question mark 3 times the fourth root of 256 is 4? Does 4 minus 8 equals 3 times 4? Carson, you? No, it doesn't. What's going on here? What, did we mess up? Did we mess up? No. Where in our work could we have seen earlier that there be no real solution? Right? Where in our work? Which colored line here would show that there be no real solution? Ben C?
Like the step before you did to the fourth power.
So this black line -4 to equals fourth root of c. Why do you say that step?
Because it's even with x is negative.
Absolutely. Right here with an even index radical set equal to a negative output, that will never happen in the realm of real numbers. So we could have forecast that there'd be no real solution. We generate a potential value. It does not satisfy the original. So what is that called? Right, what do we need to label that on our test? What is that called? Mark?
Extraneous solution.
Absolutely. It's called extraneous. It doesn't satisfy the original. It's extraneous, and it's not a solution at all. If that's an extraneous solution, then what do we say? We say no real solution. No real solution. Awesome. What questions do you have about undoing our radicals? Then go ahead and show me you get it with number 4 and number 5, and be ready to share your results on the whiteboard. Okay? Go ahead and show me you get it with number 4 and number 5. You may do this with your partner. Check with your partner, and be ready to share on the whiteboard.
You should wait to subtract during
So we can't get into subtract point until we undo radical. So you get that formula and then lastly. Okay, ladies and gentlemen, let's go ahead and come together and check our potential solution values. And so right now, raise your hand if you got the potential solution C equals -3 for number 4. C equals -3 is potential, good. Raise your hand if you got F equals 7, potential solution for number 5. Okay, so how do we know if we should box these or not? What should we do procedurally before boxing these? Taylor?
we can check it like a
Thank you. Let's go ahead and check each of these in the original. So for number 4, I'm going to plug in -3 and for C in the original, work it out. You guys can help me. So here we go. -3 plus 2 is -1. The 7th root of -1, Can I have a negative inside of a radical? I can if it's odd. The 7th root of -1 is -1. Does 21 plus a -1, 22 plus a -1 equal question mark 21? Yes, it does. So this is in fact the solution to my radical equation, and I'll feel comfortable boxing it C equals -3. We'll do the same thing for 7. Let's go ahead and take 7 and plug it into my original everywhere I see an F in number 5 and work it out. Here we go. 7 plus 1 is 8. The cube root of 8 is 2. 2 times 16 is 32. Does 25 minus 32 equal question mark -7? Does 25 minus 32 equal -7? Yes, it does. And so we have generated a solution to the equation F equals 7. In each of these cases, there appears to be one real solution. Could we have seen that? Could we have forecast that earlier in our work? Yeah, where could we see that we'd expect one real solution? Margot?
The green.
Yeah, the green right here, the cube root, isolated, set equal to a positive, we expect one real solution, right? The 7th root of right here, isolated in blue, set equal to a negative, that's okay. It's okay to have an odd index radical set equal to a negative number, right? We saw that. So it's okay to have an odd index radical set equal to a negative number. There's one real solution. So that was our number 12 that I told you guys to take a look out for in the beginning. Awesome. You guys have done great work today. Let's go ahead and do our closure. So with your partner, quietly decide how you undo the radical below. Then we'll list in order the 7 steps to undo and solve for x in that following equation. That's a big bad mother daddy of them all. Closure question number 2. And then as a follow-up in number 3, looking at number 2 above, what values of n, the index on my radical, could generate extraneous solutions, right? Extraneous solutions. Go ahead and work on the closure with your partner. And then we'll come back together to check.
First, we start outside, so you're one over I say you would have to subtract just W. Doesn't matter. Yeah, some people think X or it's less.
Okay. Let's go ahead and check. Let's go ahead and check our closure answers then. Please share with the whole class when I call on you. How do we undo? How do we undo that radical expression to solve for x in number 1? Go ahead and share with the class. Olivia B.
Bring it to like the nth power.
Absolutely. We're gonna raise it to the nth power. Not the 1 over nth power. This current exponent on the x, right, is like a 1 over n. To undo a 1 over n, you have to raise both sides to the nth power. So we're gonna raise both sides to the nth power to undo an nth root radical. Good job, thank you. Now we're going to list in order the 7 steps that would undo and solve for x in this following equation. We've got a whole list. So let's see if we can do that. 1, 2, 3, 4, 5, 6, 7. I'm confident we can do it. Here we go. We want to solve for x. Get at that x right there. The first thing we better do is get rid of that multiplication by r. So first step, divide by r. Next step, we'd have to subtract over that w to isolate the term with the radical. So minus w. Third step, undo the multiplication by b. Oh, that's division by b. Now we have the radical alone. How do we undo an nth root? What do you do procedurally to undo an nth root? Ben C?
Sorry.
How do I undo that nth root?
The M.
Absolutely. I'll write that as raised to the nth power. Thank you. After I've undone the radical, I need to get rid of the fraction. Divided by p, so I need to times by p. I better write that with an asterisk. Times by p. Now I've got quantity k minus ax alone, so we better subtract k. And lastly, to get the x by itself, I'll divide by negative a. So dividing by negative a would be my final step. Now we get the x alone. Woo! That's a whirlwind. In the course of solving this equation, we could have determined if there would be extraneous solutions in one of these steps, right? And which values of n could result in extraneous solutions. So what would n have to be if we're going to result in extraneous solutions? Marina? Yeah, if n had been even, then we'd be dealing with an even root. And that was the only example where we ran into no real solutions or generated extraneous solutions. So if n were an even root, right, set equal to a negative number, then there'd be extraneous solutions. If n were an even root set equal to a positive, then we'd expect one real solution, just like the odds. Great work today. You guys are going to have an opportunity then to work on your assignment 8, and we got a big chunk of time. Please make sure you're using this time for advanced algebra. And no more reading questions for the unit. And so we've got a nice chunk of time. I'll go ahead and pause and upload the recording. Nice job today, ladies and gentlemen.